guys, welcome back to In Case of Econ Struggles. Welcome to another game theory struggle. Today we're talking about infinitely repeated games, subgame perfect Nash equilibrium, and Bayesian Nash equilibrium. It can be pretty tough to figure out the solution to an infinitely repeated game. It can be tough to figure out exactly what the question is asking, and it can be tough if you don't have a lot of tools in your toolbox for solving infinitely repeated games. So that's what I want to do today. I want to give you some tools in your toolbox for some common infinitely repeated games like the Prisoner's Dilemma. And then I just want to go through a couple other tips and tricks that might help you if you get to a question that you haven't seen before and you need to find the Nash equilibrium or prove that something is a Nash equilibrium for a given game. So timestamps are below, but here's what we're going to do. We're going to start with tip 1, which is about creative strategies, and we're going to apply that to the Prisoner's Dilemma game. Then we're going to play this game called Take It or Leave It, where my second tip is going to be to use rules as strategies to really get creative and really use the definition of what a strategy is to help you out. And then we're going to play Pet the Angry Cat to also show you how you can get creative and that the number of players might matter when you're solving a given game. So again, timestamps below if you would like to jump around. Let's start off with the Prisoner's Dilemma. So here is an example of an infinitely played Prisoner's Dilemma. And so in each round, you're going to play the standard Prisoner's Dilemma. So I've just defined those payoffs in the box right there. Now you have Bill and Deb. And so remember that a Nash equilibrium is a strategy such that both Bill and Deb are best responding to each other. So there's actually an infinite number of subgame perfect Nash equilibrium to this game. And so I want to give you a couple common ones that you can use that might come in handy either for the Prisoner's Dilemma specifically or for a similar sort of game, even if it's not called the Prisoner's Dilemma. So I'm going to have 3 strategies. Strategy 1 is going to be Grim Trigger. Grim Trigger with Forgiveness is going to be strategy 2. And Tit for Tat is going to be strategy 3. I'm going to explain all of those in turn, but that's just so, again, you can jump around if you sort of know one of these, but not the other. Here's the Grim Trigger strategy. I'm going to cooperate, but if you defect on me, then I'm going to defect on you forever. But if you play Cooperate, return to 1, and I'm going to play Cooperate in the next round. So notice that I'm really using the broad definition of what a strategy is, because I'm not saying, oh, I definitely play this or I definitely play that. This is a strategy that I follow in each round into the next round, but it is still a strategy, and if this strategy is my best response to the other person's strategy, then this is going to be a subgame perfect Nash equilibrium. So what we're trying to show is that both people playing a Grim Trigger is in fact a subgame perfect Nash equilibrium. So what we're going to say is that, well, if for this to be a Nash equilibrium, for this to be a best response, both people must want to cooperate. They must not have an incentive to defect. So suppose that Bill is going to decide to play this Grim Trigger, and suppose that Deb is going to defect. It's a symmetric game, so we could do this either way. Suppose Deb is going to defect, and if Deb is going to defect, it makes the most sense for Deb to defect in round 1. So if she defects in round 1, she gets 0 years in prison because she pins it all on Bill, and Bill gets 10 years in prison. But then for the rest of the infinite future, Deb is going to get 5 years in prison because you can see that what's going to happen is that Bill is going to defect all the time, and if Bill is going to defect all the time, Deb is also going to defect all the time. So we're going to collapse into this square right here. And since we have this time discount factor delta, it's going to be delta to the t. And so this is going to be what our payoff is for Deb if she defects in round 1. But notice that if she does not defect in round 1, if she chooses to cooperate in every round, she's just going to get 1 year in prison in each round, which using our geometric series rule, we get minus 1 over 1 minus delta. And so for this to work, what needs to happen is that this payoff needs to be better than this payoff, so we can just set it up and solve it mathematically, and we're going to get that delta has got to be greater than 1/5, which is a pretty low delta. We're probably going to have that, but notice that it's important because we need the caveat that this is a Nash equilibrium, this is a subgame perfect Nash equilibrium, only if delta is greater than 1/5, and that's for Deb, but also for Bill because it's symmetric. So really what this is going to be is this is going to say that delta Deb needs to be greater than 1/5 and delta Bill needs to be greater than 1/5. And if that's true, then the Grim Trigger strategy is going to be a subgame perfect Nash equilibrium, and that's how you show that. Now we can also play a different strategy on the Grim Trigger, which is Forgiveness. And so in this context, again, we're going to start off with I play Cooperate. If you play Defect, I'm going to play defect until I see you sort of repent. So if you decide, oh, I messed up, I'm going to play cooperate, I'm going to take the hit, I'm going to get the 10 years in prison, but because I'm getting the 10 years in prison, I'm sort of convincing you that I'm ready to cooperate again. And so if you play cooperate, then I'm going to play cooperate, and we are going to go back into this strategy. So again, we can see that what's going to happen is we are going to have to figure out what does the patience, what does the time discount factor need to be of both people in order for this to be a subgame perfect Nash equilibrium. Just to make it easy, I just said, well, let's talk about it with 3 rounds. And so if we talk about it with 3 rounds, and you could do this off into the infinite future, but if Deb decides to defect and then repent, notice that she's going to have minus 10 delta for getting the penalty, and then 5 delta squared. Is Grim Trigger with forgiveness a subgame perfect Nash equilibrium? What conditions do you need for that to be true? You would solve this and you would say it is if delta is greater than 1/2 for both Bill and Deb, because again, it's a symmetric game. So if this is confusing so far, please leave a comment below, but also if it's helpful, please leave a comment below as well. Now another strategy that you could do is you could just say play tit for tat and just play what you played last time. So I think it'd be useful for you just to see if you can work this out, see if it makes sense to you to figure out if this is a good strategy or not. And if you've got questions about how to do that, leave comments below. If I get enough comments about doing the solution to this, then I'll make a separate video where I work this out. But I sort of wanted to leave this for you to try on your own and to see if you can really get the hang of how this works. So again, if you can't, leave a comment below, but if you can, if you work it out, if it all makes sense to you, and this is helpful, again, comments are useful. So now that we've covered Prisoner's Dilemma, let's cover a new game. This is called Take It or Leave It. Here's how the game works. There's an infinite number of players. Basically what happens is there's $1 on the table, and 2 people are playing until someone says stop. And what's going to happen is if you say stop, you are going to take the money that's on the table, you're going to stand up, you're going to leave the game, there's a new dollar that's placed on the table, and someone new from this line of infinite people steps up to play with you. If you say go, the person you're playing with has the option to stop or go, and I add $1 to the pile on the table. So, for example, if A chooses go, and B says stop, B takes the $2, then it's A's turn because A is still in the game. So maybe A chooses stop and takes the $1, and so now A is gone and player D steps in. So now it's player C and player D. If player C says go, player D says stop and takes $2, and then player E is going to step in and play with player C. So first, let's think about an easy question. Is there a subgame perfect Nash equilibrium where everyone gets $1? Well, of course there is, because everyone can just say stop and take the $1. So that is a situation of subgame perfect Nash equilibrium where everyone says stop. And I think it's pretty clear that that's a subgame perfect Nash equilibrium. You could probably just explain that and get full credit on a test or exam. A hard question, on the other hand, would be, is there a subgame perfect Nash equilibrium where everyone gets greater than or equal to $2? So now how are you going to figure this out? Well, you could say that yes, there is, and you're just going to make up a rule, and the rule is that you say go if the pile is less than $3. So you basically, the strategy here is if money is going to be less than $3, then go, else stop. So that is going to be your subgame perfect Nash equilibrium, is that everyone is playing this strategy. How does this work? Well, suppose that you said stop when the money was at $2. Well, if you say stop, the money is $2, then there's no reason why you can't just say go. Because if everyone's playing go, if the pile is less than $3, then the person across from you is not actually going to say stop if the money is less than $3. So you can just stay in the game, wait until it's $3, say stop, take the money, and then we'll just keep going and everyone will get exactly $3. And you could also do the same strategy with 4, with 5. You could do this for any amount of money because everyone will be incentivized if they're playing this strategy. No one wants to deviate from this strategy. They're all best responding to everyone else. So it is, in fact, a subgame perfect Nash equilibrium. Now notice, again, as we start getting into some of these tricky sort of subgame perfect Nash equilibrium concepts, there's a lot less math and a lot more thinking about it. You could definitely do it with math, but I think with game theory, we're getting to the point where it's going to be a lot of words, a lot of making sure things make sense. Some programs might require additional math, and if yours is one of those, leave a comment below, and I'll do a version of this as well where I do some more math. But I think intuitively this is making a lot of sense and hopefully helping you get a feel for how these sort of infinitely repeated games work. Finally, for our last game, let's play Pet the Angry Cat, where you've got more than 3 people. So here's how this game works. So it's a simultaneous game, everyone decides at the same time. Your 2 options are to sit out, and if you sit out, you get 2 points. Maybe you get an entertainment value for watching other people try to pet this angry cat. And then if you try to pet the cat, basically we figure out who has decided to try and pet the cat. So maybe if this person, and this person, and this person all decide to pet the cat, then what we're going to do is we're going to select one of these 3 random people. They're going to get to pet the cat. They get +6 because they enjoy petting cats. And because this cat is going to hiss at all the other people who try to pet it, they're going to get 0. Just because the cat's not actually going to attack them, it's just going to hiss at them, and they're sort of sad that they don't get to pet the cat. So now, suppose that we're trying to ask the question, is there a subgame perfect Nash equilibrium where no one tries? Well, suppose that I try and everyone else doesn't. Then I get 6, and that's way better than the 2 if I were sit out. So this is no one else tries. The payoff of me trying, given that at least one other person tries, or exactly one other person tries, is going to be a half chance that I get 6 and a half chance of 0, which is 3, which is greater than my payoff if I sit out. But as soon as 2 other people try to pet the cat, then my expected value or my expected payoff of trying is exactly equal to my expected payoff of not trying. And so the Bayesian Nash equilibrium is that if I think at least 3 other people are going to try, I'm going to sit out. And if everyone thinks that at least 3 other people will try, because again, it's a Bayesian Nash equilibrium, it's based on our beliefs. So if we all think at least 2 other people or at least 3 other people will try to pet the cat, then we're all going to sit out. And if we think that no one else is going to try to pet this cat, then we are going to want to pet the cat. Is this still true if n equals 3? No, it's not true. And I want you to think about this again. I want you to think why this isn't true. See if you can figure it out. Leave a comment below if you think you've got it or if you're just confused and can't figure it out. And again, that'll be part of the follow-up video where I sort of explain why that's true. But hopefully this is getting you well on your way to understanding some of these more complicated games. Some more tools in your toolbox to help you solve game theory questions on homeworks and exams. If this is helpful, please like and subscribe. We'll see you next time for another case of econ struggles.